All right.
Yeah, you can start.
Perfect. So I'll just stand here with. Okay. All right. So yeah, welcome to this session on multiple regression. Now, of course, we won't be able to cover everything. Like I know multiple regression is a very extensive topic, but I think what we are going to do today, the plan is to cover the important concepts, because once you have the building blocks, the foundation, you'll be able to build on that, moving forward, right? So we are going to focus on the important concepts of multiple regression. Now, as we always say, the most important thing, one of the first most important thing is to understand when do you use multiple regression. In other words, what type of research questions do you address using multiple regression? Use it like different ways to phrase or to craft your research questions. But here what I have is just a couple of examples in which you can craft your research questions to address or to be able to use multiple regression. Now, keep in mind the reason why it is called multiple regression is because you are dealing with more than one independent variables. That's why it's multiple, it's more than one. And in regression, independent variables are called predictors. So you're gonna hear us talk about predictors, talk about independent variables is the same thing, right? So more than one predictors in multiple regression. So for example, if you are interested to find which independent variables explain a significant proportion of the variance in the Y is our dependent variable. So in the notation for regression, we use X for predictors and Y for dependent variable, right? So if you see X, you should know that it stands for independent variable or predictor, and Y, it stands for the dependent variable. So some of you I've been meeting this morning, you were interested to find which factors, some were asking in terms of factors, is the same as independent variable. So which factors explain a significant proportion of the variance in the dependent variable? We are going to see that when we do multiple regression, one of the things we are interested in, or the most thing we're interested in, is to find out how much change in the dependent variable are we explaining using our predictors. So we are going to talk about the proportion of the variance. How big is that variance? How much are we accounting for, right? That's one thing that prediction or regression does, to be able to explain the changes in the dependent variable based on the predictors. Another scenario, how much variance is uniquely explained by each of the independent variables. Okay, we are going to be looking at this as well. Multiple regression, you are looking at multiple predictors. So in addition to looking at collectively how much the independent variables are accounting for variance, you're also interested in looking at individual predictors, because some of those predictors might be doing the job, others might not be doing anything. And so you want to be able to say each predictor, how much variance unique is that predictor accounting for in the dependent variable. Okay. Or also, does a particular variable or set of variables add to the explanation in the dependent variable above and beyond what is already explained? So we are going to be talking about hierarchical regression, right? You put in one variable, you put it another, right? In addition to already what's being accounted for, how much is the additional is explaining or accounting for? So we look at hierarchical. So depending on what you're interested in, you can see like you can craft your research questions accordingly, right? As I said, like talk about what predictors explain this, what factors influence this, you might use different wording, but at the core of it, in the end, you want to find out which of these predictors explain what's happening in your in your dependent variable. Okay, so just to show you visually, is it a question? Oh, okay. All right. So now, to show you visually what we are essentially doing when we do multiple regression, look, those Venn diagram, you have your y, okay? This is your dependent variable, right? X, in this case, you have x1 and x2. These are your predictors. So the ideal scenario is you want each predictor to account for unique variance. You know, the red shaded area is how much unique variance is accounted for by each of the predictor. So x1 is accounting for this variance, and x2 is accounting for that variance. And look, the correlation between x1 and x2 is 0. That's a perfect scenario. Kind of in a perfect world, that's what we want. We want each predictor to account for unique variance, right? In the dependent variable, I'm going to show you, we are going to see a situation in which you do not have a unique, I mean, you have some unique variance, but also you have some overlap between x1 and x2. And that scenario you're going to see, there's a way for us to test for it in regression, because we do not want our predictors to have some redundancy, right? Because if there's redundancy, it means we are not going to account for a big chunk of the variance, right? I mean, I'll just give you a practical example. Let's say we are doing a task in this room. Someone is cleaning the floors, the carpet, someone is cleaning the windows. Now, for us to accomplish a lot of work, each one will need to do different piece of work. If you come and do what I'm already doing, I mean, we are not going to cover a lot of ground. We will need you to go and do a different piece of work, so that collectively we are going to cover a lot of ground. That's the same thing that happens with oh, this is right. Oh, okay, thank you. Yes. All right. Thanks. Right? So that's essentially the same thing with the regression. We want each predictor to account for unique variance in the dependent variable, so that collectively they are going to cover a lot of ground. So when independent variables are uncorrelated, proportion of variance explained by each is simply r squared, right? So what we just seen here, okay? So if we calculate the variance of this, we are just going to take the correlation between x1 and y, we square it, and the same thing, correlation between x2 and y, we square it. It will tell us how much variance. You're going to see, we talk about, is it 20% variance, 50%, 30%, and so forth. We talk about the proportion of the variance which is being accounted for. So essentially, that's what that is talking about. Yes. Yes. So now you're saying when the independent variables are uncorrelated. Yes. Does that mean they must not? Yes. Good question. So, well, but in real life, in regression, you're not going to have zero correlation. There's going to have some correlation, but we are saying we want the correlation between predictors to be low. So in an ideal scenario, in a perfect world, the correlation is going to be zero. But again, we understand that's not going to happen. So there is actually a way to test how big or how small is the correlation. Because again, the lower the correlation, it means the stronger the model that we are going to have when we have a low correlation. Yes, yes. So yeah, we need low correlation. If they can be independent, or if they complete, that would be even better. Okay, so now, when independent variables are correlated, we take into account the overlap. Okay, so show you visually how it's gonna look like. This scenario here, you see, it is less desirable. Look now what's happening. You are seeing that x1 and x2, they now have this area here which is overlapping between the two of them. So you see, this now the unique variance for x1 on y is the yellow area. The unique variance for x2 and y is the red area, and this one here is the common variance between x1 and x2, right? So now you can see that if the more they overlap, it has an impact on reducing how much they are contributing to y. So that's why we say we want this overlap here to be as small as possible. So your regression model, one of the ways to evaluate whether it's a good model is we test our predictors. How much overlap do they have? The smaller the overlap, the better the model, because what it means is if this overlap is small, their unique variance on y is going to be bigger. So kind of that's what's going on when we do our regression model statistically. So again, you can see that the correlation between x1 and x2 is not equal to 0 because they overlap on this. So we'll be talking about what that concept is and how to test it for in regression. So you remember we were talking about, I don't know who I was talking to in the morning about predictors. I think it's you, right? Remember, we were deciding whether you should combine them or whether you should treat those constructs separately. And one of the things I said, it depends. If you run a correlation, if those individual constructs are highly correlated, right, it means they are measuring the same thing. So when they are not strongly related, then they are measuring something unique to, and then it makes sense to use them separately. So that's how you kind of make those decisions. Yes.
Just like something now, if they are strongly correlated,
yes,
you can combine them together as a construct. That's why I say
yes. So let's say I'm measuring A and B, right? And A and B, the correlation, let's say 0.90. That's very high, right? So if I were to draw that, they are also almost the Venn diagrams, they are going to have a big overlap. So it means they're measuring the same thing. So if I use them separately as predictors, I'm going to have a lot of redundancy because they are accounting for the same thing in the dependent variable. Okay, and that concept is what we call multi-collinearity, which is the next slide. Some of you might have heard of that term, not, but multi-collinearity is a situation where your predictors are highly correlated with each other. And we are saying in regression that's not desirable. We don't want that. So if independent variables are too correlated with each other, it can lead to inflated standard errors. In other words, we are saying our model becomes less accurate. Because it goes back to what I told you earlier, it means these predictors will be doing the same job or they are redundant, right? So if they are redundant, it means they become less efficient, yes.
So in terms of research questions, does that mean you write it to be, if there's much collinearity in terms of research questions, does that mean you're asking essentially the same thing in two different questions?
Yeah, exactly. You see, so yes. So essentially, in simple terms, that's what you're saying. Like, let's say you have, two variables measuring, math achievement and academic achievement, however it defined. I mean, someone who is likely to be smart in math or do well in math, they are likely to do well academically. So if we take correlation between math scores and academic, they are likely to be highly correlated, right? So if we measure those as predictors, I mean, it will almost be redundant because we'll be asking the same thing, right? So it's essentially like that. So, but statistically now, we are saying there's a way to test whether your predictors have some multi-collinearity or not. And here's the challenge though. When you state your research questions up front, you don't have access to your data. You haven't collected your data. So you don't know whether this, but you might know maybe from literature or from your knowledge, from conceptual knowledge of what you are measuring, you might have an idea. But until you test for it, then you are going to be able to tell that, oh, okay, I have a problem here of multicollinearity. Then that's when you have to make a decision. Should I drop one? Should I combine them? Should I do what? Based on what you are seeing on the test for multicollinearity, right? So highly correlated independent variables, of course, can result in R square. By the way, R square, there is a coefficient that we use to measure the proportion of the variance. We are going to take a look at this once we get to the SPSS. We calculate one of the ways in which we measure the quality of our model is to look at how much R square are we accounting for. In other words, how much variance is our model accounting for. The larger the R square, the better the model, right? So we are going to be taking a look at that. One of the ways to do to check whether you are likely to have problems with the multicollinearity is just to obtain simple correlation, Pearson correlation here. Take your variables, run a correlation, you see, but it's not an accurate measure. We are going to take a look at accurately how do you. It's a quick check to say, you know what? Okay, do my variables look like? Do my predictors look like they are highly correlated? And if not, okay, you can confirm that with another test which you are going to take a look at, or if they are, then again you can also confirm those with that test. Yes. Oh yeah. So you're writing down. Okay. So so questions on multicollinearity in terms of what it is and why it's important. In simple terms, again, keep in mind it's redundant. We want our predictors
Excuse
to
me.
predict.
Excuse me.
Is it a yes?
Yeah. It's a question on Pearson
Yes.
correlation. If I heard you correctly.
Okay. What is Pearson correlation?
No, you had said that it's not a reliable way to measure multicollinearity.
Oh, yes. Okay. So I'm saying, like, Pearson correlation is a way you can use to, just, a quick check to see whether your predictors are related or not. But when we do regression, there is a more definitive test that we use to determine whether multicollinearity is a problem or not. But kind of consider Pearson correlation to be a starting point. Because sometimes you might conclude that, oh, okay, my predictors are not correlated, but once you get to check with collinearity diagnostics, you might realize that, oh, you know what, you have an issue with the collinearity, or you do not have. So all we are saying is consider that Pearson correlation to be a starting point, which you can use to give you idea of whether you might suspect that you have some collinearity between your predictors.
Okay.
I don't know if that answers your question or if that is what you were asking.
Absolutely, it answers. Thank you so much.
Okay, perfect. Okay, so, okay, let me see this here. Okay, we talked about this. And then, now, how do we testing for significance? You see, you are going to see that when we do regression, right, we get the overall results, like results of the entire model. I'll show you where to go and interpret that. And in addition to that, we also have a table which shows that individually, which predictors, you remember, right, what we did in the morning, you had 4 predictors, but out of those 4 predictors, one was not significant. All the others were significant, but so you'll be able to see which individual predictors are actually contributing to the overall significance of the model. You see, so the t-tests, they test for those coefficients, or be able to show you where we get those t-tests and how to interpret them. Keep in mind, when we interpret these results, always we look at the p-values. Yes, p-values, p-values. So we test this at p-values of 0.05. So we look and say, okay, is it less than 0.05, is it greater than? So whether you are evaluating the overall model or whether you are looking at just individual predictors, compare that to 0.05. If it is less than, then it is significant. If it is not, I mean greater than, then it is not significant. Okay, so now,
sorry, Prof.
Yes.
Before we start this regression.
What's that?
When you said before you start this, when you started, you said multiple regression.
Yes.
Now, there is this they call multi-level analysis.
I know. Yeah.
And they mix them up like this.
Yeah.
Multiple regression,
Yes.
hierarchical regression.
Yeah, that's a good question. You see, the thing with the statistical models, there are some different levels depending on the level of complexity. So what you are asking about is what we call multi-level modeling. It is also called hierarchical linear models. It's different from hierarchical regression. So the hierarchical linear models, what they do is, I want you guys to consider data which is usually found in schools. Because if you think of schools, students are clustered in classrooms, right? And those classrooms are nested within schools. And the schools are nested within maybe school districts. So if you look at those type of data, those data are multi-level. They are different levels. You can collect your data at the student level, and you can collect your data at the school level, or you can collect your data at the district level. So if your data are in that hierarchical fashion, those type of models are called hierarchical linear models, or they are called multi-level models, of which we are not going to discuss them.
So those ones you can't use regression.
No, you cannot. You cannot, because regression models, they assume that the data are only collected at the individual level. Yes, if you are measuring students, you have individual student scores. You don't have information about the school level data or the district level data. So you do not have what we call nested data or hierarchical data. So yes, we can't use regression for those. So in this case here, we only are looking at data which is measured at that individual level. So we are not going to use those multi-level data models or hierarchical linear models. And actually, SPSS cannot do those high-level models. You would need specialized software like HLM, maybe even Starter, and some other software that use those type of models. Now, here we are talking of hierarchical regression. It's not the same as the hierarchical linear models. Hierarchical regression we are talking about here is, let's say you have predictors. Predictor 1, predictor 2, predictor 3, right? And the order of importance of those predictors, based on theory or based on literature, you maybe suspect that this here is more important in accounting for the variance. So you are gonna enter that first in the model. So in other words, this hierarchical we are talking about here is the order in which you enter your predictors in the model, not the nested nature of the data. See, so hierarchical regression is a concept closely related to partial correlation. It's a procedure used when you conduct the sequential testing of either single variables or set of variables. The question is, how do you determine that sequence? And the answer is, it is based on your knowledge of the predictors, right? Maybe you know that maybe reading achievement is more important in contributing to academic achievement compared to maybe socioeconomic status. So you're going to put reading achievement first, followed by socioeconomic status and so forth, right? That is the hierarchy that we are talking about. And again, we have the chance to see that, how we do that in SPSS. So the main purpose of hierarchical regression is to test for the addition of variance above and beyond So you put the first predictor, you calculate how much variance we are accounting for, right? And then we put the second one, we say, okay, above and beyond what we already have, how much are we accounting for, and so forth. So we put that, we look at that variance which is being accounted for above and beyond. So look at that. It is useful in testing a new theory. So when you want to see if a variable is to our understanding of some phenomenon above and beyond what's already known, right? So does this predictor add new information from what we know? So you do some hierarchical, and of course in some when you want to statistically control, some way of controlling my extraneous variables. But that second purpose here is less common. The most commonly used reason why we use hierarchical regression is because we want to see which or how much variance we are accounting for above and beyond what we already know. Now, we are going to see we have different types of regression. I don't think I'm gonna, okay, let me hold off on that until we get to SPSS. I'll show you and then I'll explain to you the types of regression that and why or when do we use each of those approaches, because there are options in SPSS. So like what I just said, we test these variables in sequence. And we, start, the first one, the second one, and so forth. The order of testing would depend on theory, as I said earlier, right? In terms of which one is more important, and you will likely be determined in large part by your literature review, your understanding of those predictors. Then you decide which order to put them on. And of course, order should also follow logic, where applicable, right? Can't ignore logic in there. So an example, you want to examine the relationship between salary and job satisfaction, but you believe that the relationship may reflect a spurious associated with job status level, right? So you could enter salary into the regression equation first, then enter job status to determine how much job status is to the overall variance above and beyond what salary explains. So if the relationship is truly spurious, job status will not add anything, right? So essentially, by adding, if I'm accounting for 50% by one variable, and if I add the second one, if I'm only adding 50.5, additional 0.5, then I'll be able to say, you know what, this second predictor is not doing anything. So I'm going to drop it from regression, right? So I'll be able to determine above and beyond how much I'm accounting for and whether that is making any meaningful sense. And one of the things you're going to realize about regression is sometimes it takes some iterations, right, back and forth. You run your first model, you take a look at it. Some predictors are going to be significant, others not. So you're going to drop those which are not significant, you revise it, you go back, you run it again, and so forth. So sometimes it takes that iterations, trial and error, until you come to the final model, which you are going to say, oh, okay, this is my revised model, which you can then report on. So just depends on what you are testing and what you are trying to account for. So again, sets of variables is the same as that. No, okay. Now, what I want us to do is I shared with you, you guys, I think you received an SPSS data file, which is titled MBA. So let me see if it's the MBA .save. It's an SPSS file. So this is what we are going to be looking at. Okay. Now I want also to open this document. You should have received it also. Did you all get that file? No? Oh, okay. Maybe she said I can share with you. Let me see. This technology. Fee. Okay, so if I go to share, oh, messages in chat. Okay. Hmm. Oh, shit. Trevor, are you online? Ah, you heard me, right? Yeah. Okay. So do I add here if I wanna?
Yes.
Okay, if I want to. Okay. And they'll be able to open it.
Yes.
Okay. Mm. Because I want to share with them this file here. This one here. It's saved. I think it's saved on my desktop. No, okay, I saved it on desktop. Yeah. Desktop. And then
Says it.
MBA. So save MBA messages. Maybe. It's not showing. Yeah.
Or you can just show your screen.
Or share the screen. But will they be able to work on, like, because I want them to be able to work on the file.
Let's read the section.
Yeah, yeah. See, it's there. And then it's, yeah, file. Or it can only do PDF, PowerPoint, right? I can't,
This is Excel.
this SPSS. Can it? Or maybe share with them?
Can you convert it to PDF?
Yeah, but they won't be able to do it now because I want them to be able to, as we move along, for them to use SPSS. So I'd ask,
Because the format here is not.
yeah, it won't allow us to upload it. Because I send the files so that she can email to the student, maybe that way.
Yeah. Can you just send the file?
No, I did.
Oh, you did already.
Yeah, I sent them to her.
Yeah, and then share it via.
Yeah, if she can just send those through email, because they already have SPSS on their computer,
Yes.
they can open.
Okay.
Yeah.
Try.
Yeah, just yeah, because I shared during lunch. I told you, can you send this to the students? And yeah,
Does she have all the emails?
I think she does, right? You have received the email from her before, right? Yeah. So I should just tell her, like, the files that I send her, if she can forward those to the students, because yeah, they'll be able to open the SPSS file. Yes. Thank you. Okay, so whilst we wait for that, I want to show you what we are going to be doing here. This data set we are going to be working with is based on, I mean, not based on, but the activity we are going to be doing is based on this data. So the activity is about okay. So someone, is your mic on? Yes. And those online, you can see me, right? You can see my screen, right?
Yes, you
All
can
right.
see the screen.
Okay, perfect. Yeah, yours, I think, is still receiving echo. Okay, yeah, it's good now. Now, so let's look at this here. So we are told that for this question, our independent variables are, again, we'll take a look to see what clarity of instruction, stimulating of students, course evaluation, interests in course, instructor's knowledge, expected grade, and whether the class is required or not elective. And the dependent variable is instructor evaluation. So essentially, consider this data to be where we are trying to see what factors or what predictors predict instructors evaluation, right? Because is that a question?
No, you asked me to say what.
Oh, okay. Oh, good. Right. So consider this like, the score that an instructor, for example, gets on the evaluation is affected by things like the clarity of the instruction in the course, how the instructor stimulates students, the course evaluation interests, interest in the course and so forth, right? So we want to see which predictors is not showing online. Oh, oh. Let me see. How do I again file upload? Select. Okay, just hold on. Okay, let me see if I can.
You can share application slash screen. So if you're moving across the screen, you can
Where?
share your screen.
Here?
The second row under primary contents.
And okay, where is it? Where is it? Oh, yeah. Primary content share.
Share screen, no, share application or screen. Oh,
Oh, here. Okay. Open.
share.
Oh, see, it's not window. Is it window? Because it's not highlighted here.
It depends if you want to share the entire screen, then whatever you are doing on your screen, they will see it.
Okay. Okay, so if I do this, they'll be able to see my screen, right? If I do this, are you able to see it? No? Share no camera application. See, because the because
Maybe check on that
window.
this window.
Okay. Because you see, the thing is, window. Okay, if I do this and if I open the document, can you see it? No? See, because this one here, it won't allow me to upload my Word document. Is it only?
Yes, Prof, you can just try to share your window, the whole window, and then we will be able to see what you are working on. Prof, can you hear me?
Can they? What does it say? Yeah, this technology is just.
Yeah, they still that.
Okay, let me try this, something else. Let me try save this as a PDF. So if I save it as a PDF and
Prof is not here, so
oh, she's not here.
yeah, she wants something.
Oh.
So her office is like
Okay. That's let me see what we can do here. It's hard, but
just share the application.
yeah, I'm trying to upload because you see the thing is it won't let me share anything which is not PowerPoint or
Even if they are sharing the application.
yeah. Okay, let me see if I can open this. I converted it into PDF to see if it can upload it. So let's see. So I want to open this and share. But is it showing now? Oh, but can you read it though? It looks small to me.
The plus sign.
Oh, the plus sign. Okay. Is it better? Can you read it? Okay. Bigger. So me like that. Okay. All right. So yeah, I mean, so but if she can't also we can't do much until the students have the data set.
Yeah.
I can only show them, but they won't be able to do.
Yeah, she will send it.
Okay. Especially the SPSS, the one that .SSS, that's the one they are using. Yeah. Okay, thank you. All right, so in the meantime, now that we have the screen here, so this is what we are going to be doing, right? We are going to run a regression model in which we want to predict. Again, I'll show you the data set, which you guys, of course, right now I know you don't have, you will, hopefully. So this is our data set we are going to be looking at. Again, I know you can't see it online because this system won't allow me to share anything which is not PDF or PowerPoint. So it's not going to be very helpful for those who are online. Hopefully, you're going to receive that shortly, and then we'll be able to do that together. But these predictors here, which are listed, clarity of instruction, it's labeled clarity, stimuli, course eval, interests, instructor knowledge, expected grade, and whether a course is required or elective, and then the dependent variable is interest in evaluation. So some of you, like those I met in the morning, will see something similar, right? You had a bunch of predictors. You wanted to see which of these would predict, right? So that's essentially what you do. You have a set of predictors. You wanna, okay, which of these factors or predictors or independent variables, which of these would predict our dependent variable? So we are gonna, as we do this together, this is what we are gonna be doing to answer these research questions, and not research questions. For example, we are gonna be able to say how much variance in the criterion, and by the way, when we say criterion, it's another name for a dependent variable. So dependent variable in regression is sometimes referred to either outcome variable, criterion variable, those dependent variable. So all those, they mean the same thing. And we are gonna use the 7 predictors to predict. So as we go through this, guys, I always encourage you, think of how this might relate to your own individual situation. Obviously, this is, does not probably apply to everyone, but see, like, ask yourself, okay, for my individual, if I'm doing a regression model, which ones are my predictors? That will be an important question to ask yourself. You need to be able to identify which ones are your predictors and how are you measuring those predictors. That's very, very important. Because until you can measure your variables, doesn't matter whether you want to call it predict or what, you need to be able to measure that. Because measuring your variables, it will allow you now to quantify them, to put numbers on those variables. And once you have numbers on those variables, then you'll be able to do some analysis, right? To do some analysis in SPSS and some other software, okay? And we are gonna also be looking at the output. One of the things that you are going to find when you get these results is SPSS, it gives you what are called standardized results or coefficients and unstandardized coefficients. And I will explain the difference between the two. If you talk of unstandardized, it means you are reporting the results using the original raw scores. So if you measure, for example, test scores on a scale of 0 to 100%, when you get your coefficients, they are going to be calculated on that original scale. If it is height in centimeters, it's going to be on that original scale. If it is distance in meters or kilometers. So unstandardized coefficients are based on the original scale of measurement for that particular variable. You also get what we call standardized regression coefficients. The standardized now are the ones which we all know what standardization means. Standardized is to put everybody on the same scale. So whether you are measuring in distance using meters, or you are measuring height using centimeter, feet, or you are measuring kgs using, weight using kgs and so forth. If you are using different units of measurements, standardized coefficients, they put everything on the same scale. So that when we interpret standardized coefficients, it doesn't matter which original scale you use. So that's one of the advantages of the standardized scale units. So I'll be able to show you those unstandardized versus standardized. Honestly, there's debate in the literature. Some people prefer unstandardized units, coefficients. Others prefer standardized coefficients. It just depends on what your philosophy is. But it's important to understand the distinction between the two because it will help you to interpret accordingly. We are also going to be looking at how do we test for significance of the regression coefficients, right? Remember, we talked about all the 7 predictors. We are going to see, are they all significant? Is one significant? Two? We will be able to identify which coefficients are significant and which ones are not. And also, we'll be able to say, okay, of these, which ones are the strongest predictor and which ones are the weakest predictor by looking at the regression coefficients. We'll be looking at those. Yes, I was checking like that SPS file. Did you manage to send it to them? I know, no time for lunch. Yeah.
Okay,
So
you want me to send
yeah,
the SPSS file?
this one here. The one it says
Yeah, no, I
MB.
Well, you share the PowerPoint for the regression tools.
Yes, I already have the slide.
Yeah, the live slides.
Or I can just send the full, all those 4
Yeah,
files.
send all those 4. Yeah, this one is the one I want them to work on as we go.
Did you manage to log in?
No, I haven't logged in. I'm still using it, so.
Okay. It's okay. All right.
Okay. Okay, thank you. All right. Okay, so, and then, yeah, so we'll be able to see which predictors are significant, I mean, not significant, which are strong predictors and which are weak, and which is something you need also to be able to, when you interpret your results, you need to be able to say, you know what, even though all these predictors are significant, but this is the strongest predictor, followed by this, followed by that, or this is the weakest predictor, even though it's significant, but it's not a very strong predictor. We need to be able to reach that conclusion. And I'll be showing you where to look for that. Which variable or variables would you exclude from the model? Again, part of doing regression analysis is to be able to say, you know what, okay, which ones are not significant, you drop them out. Yeah, I mean, if it's not doing anything, why include it in the model? Because when you do regression, one of the principles that we follow is what we call parsimonious. A parsimonious model is a model which can account for a big chunk of the variance using the least amount of predictors. What do we mean by that? If I give you 2 models, one model with 4 predictors and you are accounting for 60% of the variance, and another model with 10 predictors, but you are accounting for 65% of them, I'll take the one which is smaller, right? Because with a lot of these predictors, I'm only getting 5% more. So we say our model is not parsimonious. We want it to be smaller number of predictors, but accounting for a big chunk of the variance. So exactly, yes, definitely yes. Yeah, you can revise it. You can say, okay, initially you ran, and actually I had that one of my students just last month or so. She defended it. She did exactly that. Started with this model, and then she said, okay, this predictor is not significant. So she revised it, ran it again. So until she came to the final model to say, okay, this is but you have to document all those steps and you have to report all those results to say this was the initial model. It was revised by dropping these predictors. We reran it again and this and this. So yeah, can do that.
So again, the essence of doing that is just like, if I put it this way, you're trying to actually get the real predictors that are responsible for what you're doing.
Yes, exactly. Yeah, you are, because remember, you are developing something you are going to recommend. Yeah, you are going to be able to recommend to say, you know what, based on my study, this model is good at predicting ABC or whatever you're predicting, right? So people need to be able to say, oh, you know what, okay, let me design my study maybe in the future. These predictors were recommended, so yes, so yeah, so you need to be able to say, based on my findings, this is what my final model is, and then people will be able to.
Prof, I want to take you back now because as we're talking, I'm trying to relate it to what I'm doing, and I'm still a bit of this. You know, initially, I asked about the multi-level something.
Yes.
That's why it corrected me. Now, in a, I don't know if you're familiar with this Teams study, this training.
Yeah, Teams data, yes. Yeah, yeah.
Now, if I'm working, okay, now, this is actually what I'm doing. I'm working on the Teams data, which I'm using the teacher's questionnaire to look at a particular effect of a practice in the classroom, required practice. But after sending the article out, the reviewers now were like, I should look at data from the principal and data from the teacher, and from the students.
Yeah.
Now I'm confused because initially I used a regression model.
Yeah.
But now I'm looking at data from teachers, principals, and students.
Yeah.
To look at the effect on a teacher's practice, required practice. I'm confused. Am I still using regression or
No.
going to multi-level?
Multi-level. You are, yeah, that's a good question. Now think of it. A school has one principal, right? Maybe 20 teachers. So the teachers are nested within one principal. And students are nested within teachers because each teacher might be responsible for 20 students. So students nested within teachers, teachers nested within principals. So that's a three-level, multi-level model. So you are going to collect data, or you have data at the student level, data at the teacher level, data at the principal level. So that you cannot use regression. Yes, you use multi-level modeling because it's going to model clustered data, students, teachers, and of course the principal is level 3, level 1, level 2, level 3. So that type of design, yes, you cannot use regression, simple regression, because this regression, it assumes that, remember, one of the assumptions of regression, of course we haven't talked about, the assumption is our scores are independent, right? But once you cluster the scores at the teacher level, students in class A, their scores are connected by virtue of belonging to the same teacher. Teachers in the same school or under the same principal, their scores are now maybe, connected because, see, so the independence assumption is violated. So because the independence assumption is violated, multiple regression is not appropriate to use for multi-level data. That's why that reviewer maybe recommended you to use that. I don't know again what the recommendation was, but yes. Oh, okay.
I use hierarchical linear regression initially.
Okay.
Because I was looking at them as a microsystem, mesosystem, and exosystem factor.
Okay.
But now they were not like, I'm using a framework that is very absurd to them because they are working from the American context.
Oh, okay.
So they were not like, why can't you look at this at the classroom level, student level, principal level?
Yes.
So the way they said that, then I'm like, now I don't think I'm using regression because I'm confused.
Yeah, I see. Yeah, you're exactly right. Yeah, that's a multi-level model. And yeah, usually large scale data like that. And I've used the SACMEC data in the past. Yeah, we did something similar because the data are hierarchical, they are clustered. Yeah, so, if you want to use regression, some people, they aggregate the data, right? So if you aggregate all the data and then just look at either the teacher level, ignoring the principal, right? Or you look at the student data, ignoring schools and principal, then you can use regression. But again, some people might question you that you are ignoring, the clustered data and things like that. So did you guys receive that email yet, or it's come, right? Okay, perfect. So once you receive that email, I want you guys to open the SPSS file. So of course I can't share my screen, it won't allow me to, but you should get an SPSS file with 32 cases. There are 32 people, or can consider them 32 students in this class.
sent 4 professional.
Eh?
She sent 4 files. Which one?
The one which says mba.save.sav. That's the SPSS file. The other one is the PowerPoint for today, and the other one is there are a couple of some are just like notes that of some of the concepts I was hoping to talk about. I don't know if we'll get to those concepts yet, but that's okay. And online, can you? I don't know how to check online. Any questions for those who are online? Okay.
I don't have a question, Prof, but then I'm trying to figure out where are we supposed to get the files that you are saying they've been sent to us? According to me, the latest email that I've received, they've just arrived. I've seen them now. Sorry about that.
Oh, okay. So did you just got the email with with 4 files, right?
Yes, I've just seen one now. Let me open and see what's in there.
Okay. If you look at those attachments, do you see one which is labeled mba.sav?
Yes, I do.
Yeah. So go ahead and open that one. That's the SPSS file.
Okay. Thank you.
Yeah. Is it opening up? Okay. Okay, so your data set should have 1, 2, 3, 4, 5, 6. Is it 6? Yeah. 6 columns. I don't know why you say 7 predictors. I don't think we have 7. I think we only have 5. 2, 4, 5. So, because in the document it says 7 predictors, but here is 5. So the first column should be, if you open it, is it still opening? Open now? Good. Right? Okay, good. So once you open it again, if you click on variable view, we said last week it's always a good place to start. You look at you see the names of the variables in your data set. Inst-val, clarity, stimul, knowledge, interest, cost val, and under label, you can open up to say what each of those variables stand for, right? Instruction val, evaluation, clarity of instruction, stimulation, knowledge, interest, cost evaluation. Okay, so those are our data. That's the data we're going to be working with, right? So now, if we go to our document here, now, what research question do you think we should kind of, we now know what predictors we are working with. We now know what our dependent variable, which is instructor evaluation. So you can say something like this, right? If you're somewhere to write, you can write this, or you can type it. So your research question could be something like, what factors predict instructor evaluation, or what variables, what predictors contribute to instructor evaluation of course, blah, blah. You see, something like that. So essentially, you're looking at what factors contribute to this evaluation performance, or what predictors contribute to the evaluation performance of the instructor. And if you want, you can even specify in parentheses to say which of these factors, clarity, stimuli, course eval, interest, instructor knowledge, and so forth, you put those in parentheses, right? And say contribute to structure evaluation. Now, A, so now that we have an idea of what research question we are dealing with, let's look at A. How much of the variance in the criterion, oh, by the way, ignore, it says 7 predictors. I think I deleted some of them. Let's just say predictors, because they are not 7 there. So how much variance in the criterion is accounted for by the predictor variables? That's what you are going. That's the first question we are going. So essentially, we are going to run a multiple regression analysis to answer this question. Okay. So let's go to our data set. Remember, we said last week, most of our analysis we begin from analyze. Okay. Regression, you see regression down there, kind of at the midpoint of that list. You go all the way to regression. You select linear. Yes. Oh, okay. Yeah. He is asking about the scale. Remember last week we talked about the scale of measurement in the in your variable view, that column under measure. We say like our dependent variable is always scale measured, right? Now, one thing which I didn't mention is in regression, your predictors can either be ordinal, can either be continuous, it doesn't matter. You can have categorical predictors. Gender can be a predictor, male, female, right? A continuous variable. So that measure column there, depending on how you measure your predictors, you just label them accordingly. But in this case, it just happens that all our variables, all the predictors are scale variables. So we didn't have to worry about that because they are all scale variables. They are all continuous. But keep in mind, it's possible to have a predictor which is categorical. Your dependent variable, though, always has to be continuous. Okay? Thanks for that reminder. All right, so once we are clear about our variables, then we go to analyze. We go to regression. Okay? Are we all there? Yes. Okay, good. And then linear, that's the one we want. Linear. So for those who are online, I know you can't see my screen, but again, from analyze to regression, and then you select linear. Once you select linear, you click OK, you click it. You see now you have that box which opens up, which says linear regression. Our dependent variable is instructor evaluation. So make sure you select the first variable, which is instructor evaluation. You click the blue arrow, to move it to the dependent list, where it says dependent, you put it there. And the other 5 variables, you select them, you put them under, you can do it one by one, or you can highlight all of them at once and move them where it says independence. See? Yeah, you can move everything at once, or you can do it one by one. It's okay. I mean, yeah. Right? Are we good? Now, you see under method, you see where it says method below that, where you put your independent variable, there's a small kind of box. You have method, and then it says enter. In SPSS, by default, the enter method is what you consider to be an exploratory method. What do we mean by that is, let's say you have a set of predictors, like in this case, we don't know which ones are more important than the others, right? We want to find out. We want to explore, right? So it's an exploratory. You have a bunch of predictors, but we don't know which ones are more significant. So you just put them, and then you use the default. Now, I want you, if you click that button there, the down arrow, you see you have options like stepwise. So the enter method is the exploratory. There's no particular order in which the predictors are considered in the model. Stepwise model is a sequential model which considers the contribution of the predictors to the dependent variable in order, and that order is determined by the computer. So what the computer will do is it will calculate the correlations of each predictor to the dependent variable. You remember those Venn diagrams I showed you? So depending on how large each predictor is contributing to the then it will tell you, okay, in a sequence, this is the first one, followed by this, followed by that, followed by that. Again, we are going to look at that. This is now kind of similar to what you do when you do hierarchical. The difference is when you do hierarchical regression, you, the researcher, you decide the order. You do not let the system decide the order for you. You as a researcher, you say, you know what, I'm going to enter this first, followed by that, followed by that. So you can see that the hierarchical approach, some people consider it to be even more powerful than the stepwise. Because the stepwise, we are being lazy. We are letting the computer decide for us. The same. So you see a lot of people use stepwise, but I want you to understand the difference between stepwise and hierarchical. But in terms of your results, you're going to see whether you use enter method, you use stepwise, for the most part, your results are going to be the same. It comes down to theory. How do you justify your method? In terms of, and then the other ones, you know, remove, backwards, forward, those are pretty much, we rarely use those. I mean, I've never used those, but there are also forms of sequential procedure depending on some people, like, for example, the backward is just like, you know, which one do you start entering? Do you start with the, you know, with the least important followed by the, you know, and the last one is the most important, or do you start with the most important predictor? And it's mostly like a philosophical how people view the approach. But I would say if you are doing research, you are likely to use the enter method, you are likely to use the stepwise method, and you are likely to use the hierarchical method. Now, the question some of you might have is, hierarchical is not listed here. Yes, that's a good question, right? And here is what I would show you, okay? Now, we are going to run the enter method, but after we are done, we are going to come back and I'll show you how to run the hierarchical method. Yes, yes, we are doing linear exactly, yeah. So yes, so now, once we put our variables there, I'll show you some things to obtain or to. So if we click on Yeah, let's click on statistics. I want us to, so for those who are online, on the top right of that box, you see where it says statistics. I want you to click that. And then on the kind of right side under model fit, you see where it says R square change. I want you to click that. Now, if you go all the way on that list, the last one, the last option, you see where it says collinearity diagnostics. Yes, this is where, remember at the beginning, we were talking about testing whether your predictors are overlapping or not. This is how you test for them. We are going to check this option which says collinearity diagnostics because we are going to be testing for multi-collinearity. It will give us that information. Now, you see, there's so much we kind of do in regression. We are not possibly going to cover everything, but I will show you, as I said, important stuff. I want you to click down here. We see where it says residuals. I want you to click where it says Debin-Watson. I'll tell you what that does. You see, remember, one of the assumptions we make in regression is we assume that our scores are independent. So the Debin-Watson index here, one of the things is it tests for that assumption. It looks at what we call residuals. Again, I don't want to be too technical, but I want you guys to consider when we say residuals in regression is when we do prediction, we are predicting Y from X. So if we draw that regression line, some of that is going to be directly on the line, so that if we predict Y, we are going to get what we call the actual Y value, and we are going to get what we call the predicted Y value. In a perfect world, if our regression is 100% accurate, we expect the predicted Y value and the actual Y value to be the same. So our residual is going to be 0. You get it? So the larger the residual, the less accurate the regression model. Because if your residual is 0, it means all the dots are going to be on the line. So this Debin-Watson, what it does is it looks at your residuals and see whether they are connected or they are related. So it's a measure of the independence assumption. That's what it is. And then once we run it, I will show you it's reported in the. It's a lot that we have to talk about under regression. Remember, when I was in college, I took the whole course on regression, the whole semester. That's how big this topic is. So we can't possibly cover it honestly in 2 hours. It's just so big. Yes. Oh, yes. Yeah, the larger your residuals are, the less accurate your prediction model is. Yes. So you want your residuals to be small. So when we say residuals, I want you guys to understand what we mean. Residuals is the difference between the actual Y value and the predicted Y value. Yes. Oh, good. Okay, good. Right? Now, another option below it, you're going to see says case-wise diagnostics. I want you to check that. This one here, it helps us identify what we call outliers. Some of you might have heard that term. When you collect data, one of the things we check is to see, okay, our data, does it fall within acceptable range? For example, if I'm measuring people's height, if I have a score, someone is reporting 3 meters tall, that's likely to be an outlier, right? Because it's out of the ordinary. It is out of the norm. If you are testing, so okay, so if we collect data, exactly one of the things we want to see is let's check for outliers. But the question is, how do you determine if a score is an outlier or not? It's unfortunate that some people are online, because I wanted to use the board to illustrate something, but I know they can't see. That just makes it hard on my part as well. But I will try to explain it better. If you consider that normal curve we talked about last week, you remember the normal curve? 99% of the scores under a curve, they are between plus or minus standard deviation scores. Plus or minus. So that, if you calculate a standardized scores and your score is maybe 3.5 or 3.1, it means it's outside the range, right? So in other words, we are saying one of the ways in which we look for outliers is we come here, we say, okay, anything above plus or minus 3 is an outlier. But you as a researcher, you can change this to either maybe 2.5. It's okay. But by default, 3 standard, and the question is, what are those? It means 3 standard deviations from the mean. If you are 3 standard deviations above, 3 standard below, as long as you are within those, you are within acceptable range. Anything greater than that is considered an outlier. So that's what that is. Okay? All right, so let's click continue. And then another thing, okay, some of these again, depending on time, because I was gonna show you plots and all those things. We are not gonna do that. Okay, so for now, let's select those and click OK. After we selected those, I want you guys to click on OK. And you get, of course, your regression output. Look at the first table. It tells you which variables are in the model. So that's a good way to double check. So it will tell you variables entered or removed. And it also shows you what method did you use, right? We use the enter method. See? Now, I want you to scroll down to the second table, which says model summary. Model summary, look, under that table, it will tell you which predictors we are using: course evaluation, knowledge, stimulation, interest, clarity of instruction, right? So all our 5 predictors are in there. And it also tells us what is our dependent variable. But in terms of the numbers, look, we have R.946. So the question is, what is that? We call this the value multiple R, or multiple correlation coefficient. Multiple correlation coefficient. What does it measure? It measures collectively the 5 predictors and the dependent variable. So collectively, we are saying these 5 predictors, how are they related to? So you can see it's close to 1. This value, it ranges from 0 to 1. 0 means there's no relationship, and 1 being kind of, perfect relationship. So you can see that 0.946 is very close to 1. It means that's an indication that, our model is a good model, right? Now, even better, multiple R is important, but it's not very interesting. Even better, let's look at R squared, which is the second coefficient. We take R, we square it. That's exactly what it is. The first number, if we square it, we are going to get 0.894. Now, that's what you want to look at, most importantly, in interpreting your regression model. Because what it means is, if you convert this into a percentage, that's about what? 89%. So it means your regression model is accounting for 89% of the variance. In this case, we are saying those 5 predictors, they are accounting for 89% of the variances in structure evaluation. Right? Yeah, combined, exactly. All 5 collectively. We haven't seen, we'll get there to see which ones are doing the work, right? So all 5 collectively. Okay, and then, of course, you see there's also adjusted R and so forth. So those usually they are close, The adjusted R is usually like, adjusting for statistical noise and things like that, but they are the same index, they are the same measure. So we focus, some people, well, if it is a good model, those are usually within the same ballpark. Yeah. So whether you interpret adjusted R or R squared, adjusted R squared or R squared, it will still give you same conclusion, right? Now, but I want you guys to go to p-value. Yes. If the R is, yes, so the R is telling us that collectively the 5 predictors, they are highly correlated. Why do we say highly correlated? Because it's close to 1. Right? Yeah, the thing is, yes, the R, it's just for us to know what's going on, but what's more important to report here is your R squared. Because R squared, now it talks about the proportion of the variance. In other words, it's telling us how good your model is. I remember yours, we got what, 20%, which is still good for observational data. I mean, anything like, 15%, 20%, it's a good, if you are doing a regression model using survey data, that's a good model, right? So that's how to interpret that. You contextualize it on what you are measuring, but look at your R squared and you interpret in terms of the proportion of the variance that you are accounting for in the dependent variable, right? So now I want you to look at the ANOVA table. Under the ANOVA table, look at the p-value, which is the SIG column. The SIG column, p-value is less than 0.05. So it means to us that overall, the model is significant, overall, okay, which is good. So we know our regression model is significant. Now, if we scroll down where it says collinearity there, this is where now you look at individual predictors. So if you look at the coefficients, you see the first column there, B, unstandardized coefficients. You see unstandardized coefficient, and then you have a B and a list of those numbers there. Negative 0.443, 0.386, you see that column? Remember, I talked about the unstandardized coefficients earlier. That's what those are. In other words, they are the original score that, remember this, but let's assume that, these surveys were responded on a 1 to 5 scale, maybe, I don't know, right? But so like at scale from strongly agree to strongly disagree, whatever that scale is. So that's the original score, what is reported under the standard unstandardized coefficients. I want you to go from that column, move 1 to the third column to the.
There are some articles that normally report this statistics, is it variance, inflation, PIF, and this will be narrative tolerance.
Yeah, I'm getting there. Yes. Okay. So after unstandardized, then let's go to the standardized beta coefficient. You see that third column? Yes. So the difference is, again, the standardized, they are exactly standardized. They've been put on the same scale. To the advantage of standardizing is it becomes easier to interpret because they are all on the same scale, which in this case, I will be able to look at them to say, okay, the most important one or the most important predictor is the one with the largest standardized score, right? So if we look at those values, the first one is 0.523, then we have 0.269, 0.215, 0.011, 0.243. Which of those 5 is the largest value? It's 0.523, right? Yes. So I'll be able to say this one here, 0.523, is the largest of them all. I mean, it just happens that it seems to correspond to also the unstandardized, but it doesn't always follow, because in this case, our unstandardized, they are all measured on the same scale. So it kind of corresponds. But consider if you are measuring variables, some variables are measuring height, other variables are measuring distance, other variables are measuring weight. All those are different units. But when you standardize them, you'll be able to compare apples to oranges because they are on the same scale. See, so we'll be able to say, you know what, the clarity of instruction is the most important predictor, right? Followed by stimulation, followed by course eval, and knowledge of the subject. Now that we know how to interpret the standard, I want you to go to the to the p-value column. See that p-value, sig column. Let's look at which ones are significant. Obviously, clarity of instruction is less than 0.05, right? Stimulation is also significant. Knowledge is also significant. How about interest? It's not significant. You see interest, 0.910. So if you are running this, you go and revise and run another model, removing that. You see, that will be your final model to say.
But if you remove interest in this case, won't it affect?
It will. Yeah, your results will change a little bit, but you know, yes, it will. Yeah, it will maybe. It might even.
I end up seeing another one again that will not be significant.
I would say no. I think they will still all be significant, all of them, the ones that remain. But you might see, we can do that. You might see a change in your R square. It might even improve in some cases, or it might slightly go down. But that's okay, right? Because this one here, if it is only contributing maybe 1% of the R square, you know, it's not worth including it, you know. So.
How do you calculate the percentage of each contribution of this?
Yes.
Models?
Yes, we are going to run a different analysis. I mean, either stepwise or hierarchical. Because remember, the entire method will put all of them at once. We are not able to, it doesn't give us an output which tells us how much individual each is contributing. So we are going to do another method and we'll be able to see individually how much variance each one is contributing and so forth. So we'll be able to answer that. Okay, now to your collinearity diagnostics. You see at the end of that table, those two last columns, tolerance and VIF. Those are two numbers we use to measure whether we have a problem of multicollinearity or not. Now, so you can use either tolerance or VIF. You don't have to use both because they are measuring the same thing. They are just different indices. But the interpretation is different. Did you get that column? Do you have it? The last two columns in that table, same table. You see that? We have VIF, tolerance and VIF. These are the two columns you come to look at when you want to interpret whether you have a problem of multicollinearity or not. So let's start with the tolerance. Right? For tolerance, anything which is greater than 0.1 10. I mean, greater than 0.10. 0.10 or 0.10. 0.10, right? Is considered good. So you want your values to be greater than 0.10. So if you look at your tolerance column, right, you have 0.43, all those are bigger than 0.10. So it means you do not have problems with multicollinearity. You do not have, right? If you decide to interpret the VIF column, your values should be less than 10. And again, you look at those 2 point something, 1 point something, so you don't, so whether you use VIF or tolerance, you can see that you do not have problems with multicollinearity.
So, is it possible that, because when you were talking initially, you said you can use correlation as a basis?
Yes. Yes.
Now, what if in a situation where when you do the normal correlation, they are highly correlated, yeah. But now using this VIF and tolerance, they are acceptable values. What happens?
Yes, that's a very good question. Yes, yeah. And I've seen some people who just do some correlation and say, oh, now a situation like that, I would say you would go by VIF or yes, because this test is more definitive, right? The truth is, we know that honestly, in nature, some variables can be related by chance, right? I mean, we call that spurious correlation. If you have variables which are correlated just because maybe a third variable is contributing to both of them, but the relationship between those, I've seen some crazy examples. If you go like online, just Google like spurious correlation. They'll give you examples like the correlation between snow in Colorado and inflation rate in South Africa, something like that. These have nothing to do with it, but you might find that they are correlated by chance. So what I'm saying is correlation is not definitive because it sometimes measures things. On the surface, they might look like they are correlated when they are, in actual fact, they are not. So I would say in that case, yes, you just go with VIF or tolerance, not to lie with the Pearson correlation.
Then another question I want to ask is something I've read in some articles. When they are doing this, some of them, apart from this VIF, their normal regression, they do report correlation analysis.
Yes.
Is that necessary?
Yes, I will. Yes, good question again. Because you're going to see correlation is, okay, when we do regression, one of the implicit assumptions is we are saying the predictors are correlated with the dependent variable. Because if there's no correlation, you can't do prediction. So correlation is a condition which is required for us to do regression. So by nature, when you run some regression, correlation is implied. So to answer your question, I would say yes, I've seen people like that. It doesn't hurt to include, but if you decide not to do so, it doesn't hurt either, because regression is kind of higher up than correlation. But if you decide to, yes, because it's an assumption that we make that our predictors and dependent variables are correlated. So reporting correlation, it's not bad either. Yeah, you can input that correlation matrix just like the way you report descriptive statistics, right? You always say, okay, let me report the mean, standard deviation, and so forth. You just do the same thing with the correlation.
But you don't report correlation between independent variables.
Yes, it's more, yeah. Well, you can report that.
But sometimes correlation between independent variables might be high.
Yes, yeah.
And it might not become questionable from the side of whoever is reviewing and why this,
yes.
why.
Yeah, but
because there are a lot of implications that comes up when doing this.
Yes, that's a good point. But again, I would say to that, like, as long as, or even if they are, you are going to say, you know what, yeah, even though these are correct, but according to the VIA for tolerance, multicollinearity is not a problem. Something like that, to contextualize that. Yeah. Okay, all right. So I know we are running short of time, 2 minutes, but before we go, I want to show you, so this is the enter method. Let's go back and do the same analysis, but this time let's use stepwise so that you can, let's not delete this, let's leave this output here, but let's go back to our data. We go to analyze, regression, linear. So now all our predictors are already in there. So all we need to do is to change from enter to stepwise. That's all. So select stepwise. Good. Right? And then once you do that, click OK. So this is where our stepwise regression output is starting. You see where it says you have 3 models. Right? And each model, it is telling you which variable or variables are being entered. So model 1, it is telling that we are entering clarity of instruction. Remember, this is stepwise regression, right? Let me ask you this. Why do we have clarity of instruction in model 1? Based on what we've seen previously. Exactly, because clarity of instruction is the most important one. So the computer is looking at which one has a big standardized coefficient or is contributing more. So you can see that clarity of instruction is entered first. And then we come interested. So now I want you to come here and look at this model summary. It is giving us by model, look, model 1. If you look at that it's showing you that the model 1A. You see that superscript A? I want you to go below the table, at the bottom of the table, to see what that A is standing for. A is telling us we only have one predictor in model 1. And that predictor is clarity of instruction. So you can see that clarity of instruction on its own, how much variance is it accounting for? Go and look at R squared. Look at R squared of model 1. 74% of the variance is coming from only just clarity of instruction.
Sorry, before you continue with this, I want to understand another thing here. From the first one when we were discussing, we said interest was not significant.
Okay, yeah.
If interest was not significant, then it means it should not. Will it still contribute to the variance? That's what I want to know.
Yeah.
Why it's not significant.
Yes. Okay, I see your question. Yes, and it's a very good one. Now, you see what this is doing right here is only considering the most important one. Everything else which comes in seems to have no particular order. Yes, because after entering, and you're exactly right, after entering clarity of instruction, look at interest, which is not significant, is coming second. But let's look at what's happening when we put interest there. Interest, how much interest is contributed after entering interest? We are moving from 0.74. What is the difference there? You see, if you look at R square, and actually they are giving us R square change. So the R square change is 0.743, right? No, it's 0.072. You see that? There's the column which says yeah, so interest is adding 0.072, right? Now, which again, according to this model, that change is significant. Yes, that's quite interesting. Oh, you see, these numbers, you see what I mean? So if you look at the change on the far right column is 0.002, which is significant, which is less than 0.05. Okay, let's hold on this. Let's go to the model 3 to see what's happening in model 3. So in model 3, which is C, we have put in clarity of instruction, interest, stimulation. And it's ignoring what? It's leaving out what? The two other predictors, right? Yeah, course evaluation. Yes, course evaluation and knowledge. Just hold on. Course evaluation and knowledge. Okay, which in our previous enter method, those were significant. But in this case now, those are considered not significant. Oh, quite interesting. Oh. So you can see again, depending on which model you run, I mean, honestly, I'd never encountered this, but this is quite interesting. Depending on whether we run the ender method or the stepwise, it's telling us, but the one consistent thing is we know which one is important. That's the only thing which is consistent. Everything else after that, the variables, the predictors are changing. Clarity of instruction is the one which is consistent. Now, look at the ANOVA table below that. It's telling us those three models, model 1, model 2. Now, the question is, though, of these three models, which one do you interpret? Keep in mind, model 3 is the final model, which includes all the significant predictors. Model 3 is including clarity of instruction, is including interest, is including stimulation. Okay? That's why you see all those predictors are listed in. So when you interpret this, you are just going to focus on your third model, right? And so look at everything is organized according to three models. Go to your coefficients table, right? The coefficients table, it tells you model 1, what's in model 1, what's in model 2, what's in model 3. Now, the table below that, it is telling you which variables were excluded, right? Now, here again where it becomes a bit interesting, it is telling us that in the final model, which is model 3, we are excluding knowledge and course eval. If you look at the p-value column, which is the SIG column, okay, they are both not significant. You know, yeah, I mean, honestly, like, you know, that's kind of a mystery, because you see sometimes this is where you say, like, you know, if you rely on numbers only, it's not going to solve your problem. That's why it's important to contextualize. If it were us doing this study, we would know for sure to contextualize these variables. We would know how we may be informed by the literature, by theory, but which variables are important. So that now, when a variable comes up significant, when it's supposed to, when it is not supposed to be significant, we'll be able to explain that. To say, you know what, even though this is significant, however, based on the literature, based on the theory, it's not supposed to be this way. And that's a big part of reporting your results, to contextualize them. Because you are going to get some contradictions like this for sure, right? But as long as you understand how those, how to contextualize those, that's important. So you guys see how the output for the ender method is different. I know we are 8 minutes above, but lastly, I want to run the hierarchical. Yes, the hierarchical. As you can see, the parts of the output, coefficients, ANOVA table, and so forth, they are pretty much the same. whether they run stepwise or the entire. It's just the structure of those tables which is different. Okay, so for the hierarchical, let's go back to our data analyze regression linear, right? So I want us to reset the model. Click reset button, right? Reset. Now our dependent variable is still the same. So now let's just put again, let's assume we know the order of importance. So we are going to start with the clarity of instruction first. You click that one at a time. After you put it in there, I want you to click on next. You see where it says block 1 of 1? You see there? Block 1 of 1. Huh? Do you? Or where are you at? Where are you? So if you are here, see, this is where you're starting, right? Are you here? Oh, no, okay. So analyze, right? Regression, linear. So it's the same process that we did, right? Are we good there? So it will take you here. Are we good? So you put your dependent variable, and then now I was saying our predictors now we decide, you the researcher, you decide the order. So let's say again, we know we have, it's our field, we are doing this study, we have measured the variable, and we know based on literature or theory, we know that clarity of instruction is the most important one. We're going to put it in there. And we click next. You see this next here? You click it, you enter the next variable, which is next important. Okay? Huh? What was it? What is it? Oh, interest. Was it interest? Yeah, I mean. Yeah, we can pick any. Yeah, we can pick any because you just want illustrating the. So let's pick interest, right? You put it in there. You click next. Is that good? Next, maybe we put what? Stimulation. We put next. We put in knowledge. Are we done? Okay. Let me wait. We put, how many did you put in? 4. Oh, it won't allow us to go, no. Oh, okay. We are putting, what's the 4th one? Knowledge, right? Yeah, knowledge. And then the 5th one is course evaluation, right? So we've entered them in that particular order. That's the hierarchical nature of it. So let's click OK. Oh, yeah, we're assuming that we checked it already. And oh, you know what? I'm conscious of time. Yeah, but yeah, you check statistics, you do the collinearity, the diagnostics, all those things we did. But I want to show you the output. See, it will give you for each, right? Depending on the number of variables you entered, each one will be a model. See, model 1 is accounting for, again, your R squared, okay? And up to model 5, okay? Now, if you look at the table below it, it will tell you which predictors are in each model, just like stepwise. It's the same as stepwise, but even the organization of your tables and so forth. The difference between this and stepwise is you, the researcher, are determining the order of the predictors, whereas stepwise, you are letting the computer do it for you. Another difference is here, remember, in stepwise, the computer will cut it for you. Or once you reach predictors which are not significant, it will cut. It didn't go all the way to, but here, look, it keeps going. It tells us all the predictors which are in the model, okay? And then Of course, the coefficients is the same thing. So now you will be able to look at, okay, how much is each contributing? For example, if you go to model summary, you can see that clarity of instruction is contributing 0.743 R square. And once we put the second predictor, which is interest, from 0.734, we are going to 0.802. So you can see that change. You can take the difference between those two. Okay? And so forth and so forth. So you can see which ones are contributing more and which ones are contributing less to the model. Okay. Now I know we are out of time, and I want so I can answer some of the questions in our individual meetings. I know I'm still to meet some of you, those individual meetings, but kind of in short, this is a very truncated form of multiple regression. But as I said, once you know the kind of foundation, you'll be able to kind of build on that. We haven't even talked about testing for the assumptions. I mean, testing for assumption is, I usually cover that, in my classes, like 3 hours class, the whole class on just talking about assumptions. Influential data points, right? How do we, Mahalanobis distance? We didn't get to all those things, but they're integral parts of regression, right? But, as I said, like, they're just like, I mean, we wish we had the whole day to do this, but unfortunately we don't control time. It's not on our side. But for the most part, I think we now have an idea of, how to approach it and which parts to interpret and things like that. But as I said to some of you, I'm gonna give you my business cards. Even beyond this, let's say you're working on something, I will be happy to share additional resources. I'll be happy. You can send me, say, oh, this is what I got. How do we interpret this? I'll be happy to kind of provide some, some feedback to that regard, because I know, like, we can only cover so much together. Some of this has to be done virtually. Okay? All right. Questions? I know we have gone beyond. Some of you are rushing to do some other things, but are there any questions online? Do we have any questions for you guys? Anyone questions online? I know our interaction with you guys is limited because we can't see you. You can't see my screen, but I hope you were able to follow along. Again, if you have questions, we can talk about those beyond today. Okay. All right, guys. It was nice meeting you. I wish you the best moving forward in whatever you're working on, be it your dissertation, a thesis, postdoc, a paper, whatever it is. Wish you the best, and just keep working at it. Okay. All right. Okay. Oh. Yes. Now what?
Because now
I know your paper, right?
Yeah.